about this talk, of course, is that if anything goes wrong, failure is always an option. So I can be like, it's right there in the title. What were you expecting? But yeah, we're going to talk about failure because failure is kind of a bad word, right? Like you go through school, you go through your exams, like did you pass or did you fail? What happened? Oh, the project failed, this thing didn't work. Failure has this incredibly negative connotation about it. And what I want to do in the next hour or so is I want to look at failure and the way that we understand it, the way that we anticipate it, the things that we do to kind of work with the concept of failure in the systems that we build. My name is Dylan Beattie. I've been building websites since the 1990s. I've been building distributed systems. I've been using .NET since I got Visual Studio Beta on a DVD at a Microsoft Press event in Redmond. I've been building software. I'm basically an internet dinosaur. I run a company called Versatile in London that does software training and strategy and stuff. I'm a Microsoft MVP. Run the London.NET user group. Once invented a programming language in a bar as a joke, which I'm sure some of you may have heard about because the internet quite likes it. It is the language called Rockstar. All of your Rockstar programs are also heavy metal songs, so if it doesn't compile, you can still sing it. And as I mentioned to some of you who were in the talk I did earlier, because of Rockstar now, people on LinkedIn no longer advertise for Rockstar programmers, which I think is kind of nice. Now, the title of this talk is a kind of adaptation of a very famous line from this movie, Apollo 13. There's a scene in this. Now, I'm not going to give the ending away. One, the movie's been out for like 30 years, and two, it was based on a true story. But it's about a bunch of astronauts who go into space. They're on their way to the moon. The ship blows up. It looks like they're all going to die, and then they don't die, and they get them back, and everyone goes, yay, America is amazing. And there is a scene, there you go, that's Apollo 13, like 20 words. There's a very famous scene in this movie where this character, this is the mission director, Gene Kranz. He's played by Ed Harris in the movie, and he comes out with this memorable line, failure is not an option. Now, he didn't actually say that. Or rather, he did say it, but he didn't say it back in 1961 when Apollo 13 was, 71, when Apollo 13 was happening for real. He said it in an interview with the people who wrote the movie in about 1995. They went and talked to, so the filmmakers went and talked to all the people who were involved with the Apollo 13 mission. And at some point in this interview, apparently Kranz said, you know, we realized then that failure was not an option. And the screenwriters look at each other and go, that's it. That's the strapline for the movie right there. And he liked it so much that after the movie came out, he then took that same line and used it as the title of his autobiography. But, you know, failure is not an option. By that point in the Apollo 13 mission, they'd had a crew member pull out who had suspected measles, and they're like, you can't go into space if we think you might get sick. So they'd had a member of the crew had to be swapped out and replaced with somebody else. Would they have had a backup crew standing by if they weren't prepared for failure? Well, obviously they were prepared. They'd had an engine shutdown. The Saturn V, which was the rocket that took Apollo to the moon, was remarkable. It's the only rocket that's never exploded. It's never blown up on launch, which is actually pretty astonishing as rockets go. It had 5 of these huge Saturn engines, and one of them just went, nah, not today. And you're like, we're going to the moon. Come on, can we go to the moon with only 80% of our engines? They went, yeah, sure you can. We'll just fire the others for a bit longer. It'll be absolutely fine. And at that point in the Apollo program, they had had thousands of component failures, test failures, ranging from, you know, relatively trivial components going wrong under test conditions to a fire on the launch pad that actually killed 3 of the astronauts on a mission that became known as Apollo 1. So failure was very much on the table. So what is this line, you know, failure is not an option? The Apollo Saturn launch vehicle was built to 99.9% reliability. That was the tolerance they engineered things to. You know how many parts it had? 6 million. So 99.9% meant you only got 6,000 failures on every mission. And that's normal. You know, that is their definition of success is 6,000 failures per mission is probably good enough. So to understand what we mean here by success and failure, you need to kind of take a step back. You're like, okay, we have a single hydraulic pressure valve that stopped working. That failed, take a step back, but the whole fuel pump system, well, that's got another pressure valve. So that keeps working. What if the whole fuel pump system stops working? We'll take another step back. We have multiple fuel pump systems. Those are still going. We take another step back. All the fuel pump systems are out. Well, let's take another step back. The rocket is still functional on some level, just we can't use that particular engine assembly. And one of the kind of primary drivers of this, what would become known as systems thinking, was this woman, Margaret Hamilton. She led the development team that created the software, the computer and the guidance system that took Apollo to the moon and back. And she has this fantastic quote. She said, after a while, you begin to think in terms of modeling all these things as one system. Part of it is software, part of it is peopleware, part of it is hardware. Now, the mission statement, if you like, the user story, if you're into the whole agile product thing, that took Apollo to the moon was John F. Kennedy, Rice University, 1962. We believe that this nation should commit itself before this decade is out to landing a man on the moon and returning him safely to the Earth. Now, that is one hell of a user story. Like, one, there's a deadline, the end of this decade. Yeah, that's fine. He doesn't say how we're going to do it. He doesn't say who's going to do it. It's like, yeah, we're just going to do this thing by this date. You go and figure it out. And, you know, the main rationale behind that, they needed a massive propaganda victory over the Soviet Union, and landing somebody on the moon looked like the best way of doing it. Now, when was that story actually delivered? Because you talk about, you know, definitions of success and failure. Before the decade is out, land a man on the moon, return him safely to the Earth. Well, they launched on July the 16th. They landed on July the 20th. That was the day, although in some places on Earth it was already July 21st. So like, July 20th is they landed on the moon, but then everyone always forgets the other part of the acceptance criteria, returning him safely to the Earth. Because they didn't get back to Earth for another 4 days. July 24th is when they actually splashed down. But then they had to spend 3 weeks in quarantine in case they'd brought back moon COVID or anything. So maybe returning him safely to the Earth, maybe that took another couple of weeks. By the way, I've always, there's a game my friends and I used to play sometimes where like, can you change history using the smallest number of characters? And someone suggested, what if there had been a comma in this news headline? Like, how much would that have changed? Astronauts land on the moon, they collect rocks, plant, and flag. All right, well, that would have been fun. A couple of months after this, Apollo 12 became the second mission to land on the moon, but it very nearly didn't. About 50 seconds after launch, Apollo 12 got struck by lightning twice. Now, I want you to imagine what this must have been like. You and your 2 crewmates, so you got 3 of you in this tiny little capsule, about the size of a compact car, and you are on top of 2 million liters of highly explosive rocket fuel on your way to the moon. There is a flash, there is a bang, all the lights go out, you're like, oh, this might be bad. But NASA had a procedure. They're like, okay, now the first thing that they noticed, that all these people on the ground monitoring all of the different systems, which were part of the Apollo Saturn launch vehicle, and they're looking through all these different things, and one of them says, hey, I think maybe the problem we've got here is that the ship is fine, you know, the rocket's absolutely fine, but the equipment that tells us it's fine has stopped working. And we can switch that over. They had an entire backup conditioning system. This is the guy who figured it out. It's a guy called John Aaron. And if you look closely at this famous picture of Margaret Hamilton, she is sitting underneath the control panel on the Apollo command module. And that command module, down in the bottom right-hand corner, just above where her hand is there, it has this set of switches, and one of those switches is signal conditioning equipment. Do you want to use the primary or the auxiliary power system? So the entire kind of telemetry that the astronauts use to tell the rocket's okay, they're like, well, this might stop working, so we've got a switch in here that we can use to switch it over. And they did. They switched the thing across, and it worked. All lights came back on. They got into orbit. They're like, we're just going to kind of go around Earth just once or twice just to make sure everything's okay. And it was fine. It checked out. 2 lightning strikes, absolutely fine. Off they went. They became the second crew to actually set foot on the moon. Now, if it hadn't worked, they had loads and loads of options, up to and including the launch escape system, which was basically designed if the rocket started blowing up, it would fire the command module off the top of it, it would parachute down in a field next to the launch site, and they'd probably be okay. They never had to use this. This was never tested, but you know, this is the whole point about this. The systems thinking is looking at every single component, every level of the system and going, well, if this bit doesn't work, Take a step back. Does the whole thing still operate? No. Okay, well, better put in another one of those. Take another step back. Take another step back. And so we have this kind of fractal relationship between systems, from the smallest, hydraulic valve to individual crew members to individual launch criteria, all the way up to John F. Kennedy's mission statement, which is we want to land on the moon and return safely to the Earth. Now, what you have to realize then about that famous quote is this is the context. We've never lost an American in space. We're sure as hell not going to lose one on my watch. Failure is not an option. Success has been reframed because suddenly they're like, we might become the first mission to actually have American astronauts die in space. That's not allowed to happen. We're not landing on the moon. That's gone. This is not going according to plan, but we are not going to lose one on my watch. That's what he's talking about in this context. Now, Apollo 13 actually ended up being a triumph. They didn't land on the moon, but the media attention around it was, astonishing. Some people called it NASA's finest hour. But by then, everyone was kind of getting bored. There's another famous quote in the movie, they make going to the moon look about as much fun as taking a trip to Pittsburgh. They'd beaten the Russians to the moon. The space race was over. NASA was starting to wind down the program. Public interest in spaceflight was waning. They needed something exciting to recapture it, and they came out with this. Now, this is not the Space Shuttle, because there was never anything called the Space Shuttle. This is the Space Transportation System, which consists of 3 subsystems: the orbiter, the external tank, and the solid rocket booster. But NASA can call it whatever they like. To all of us who kind of grew up watching this was the Space Shuttle. Now, the shuttle incorporated all kinds of innovations from Apollo. It also incorporated all kinds of new stuff from aviation, from aerospace. And one of the things that it incorporated, it was the first spacecraft to use a fly-by-wire system. The pilot, the commander, they would move the stick. The stick would say to the computer, hey, someone moved a stick. And the computer would be like, all right, what does that mean? It means move that a little bit, trim that a little bit, turn that engine up a little bit. And that's how they literally flew the shuttle into orbit, and then how they landed it like an airplane. Now, to understand the thinking behind the Space Shuttle guidance computer system, the computers basically got it into space and got it back again. And during launch and during re-entry and landing, a computer glitch could have been really, really bad. So to understand the engineering, we need to think about how do computer systems fail? Because failure happens in 3 different ways. You open your laptop, you try and open a website, and you have an immediate, that didn't work. Error message straight away, you tried to do that, it was unsuccessful, sorry, here is an error message. Might be helpful, might not be helpful. Or you have you try to do something and nothing happens, and nothing happens, and nothing happens, and nothing happens, and eventually you're gonna, you know what, I'm pretty sure this thing is broken, request timed out. And if you don't make the call, your browser makes the call, or your internet connection, something goes, we expected a response by now, but we didn't get one, this is a failure condition. But then you have the thing where you open your laptop and you try and read the news, and you get something that kind of looks like plausible responses, but maybe there's something wrong with it. Like SpongeBob invades Luxembourg, really? Now, when this happens, what you do is you're like, that's not right. Maybe my laptop's been hacked. Maybe this website's been hacked. Let me check it against another source of truth. So you get your phone out and you're like, all right, well, according to my phone, Biden signed a new tax deal. Let me check my iPad. Okay, tax deal. Something's wrong with my laptop because it says that SpongeBob invaded Luxembourg. But maybe your phone says Mexico won Eurovision, laptop says SpongeBob invades Luxembourg, and your tablet says that Brexit opportunities have been found on Mars. At this point, you have to conclude that the entire internet news delivery system has become unstable, and so you go and you get your news from something else. You find a different authority for the result that you need for that exercise. And that's what the Space Shuttle designers did. They anticipated these 3 different failure modes. The shuttle flew with 5 of these. This was an IBM AP101. It's basically a mainframe in a box about this big. They had 5 of these computers on board, and 4 of them ran exactly the same software, byte for byte copies of the same code. So they hired a contractor. They said, build us a guidance system for the Space Shuttle. They implemented that. They copied this, and these 4 computers ran with the same input-output bus and the same timing clock. So in theory, they always gave you exactly the same responses to everything at exactly the same moment. And if one of them didn't, you could conclude that that one, just that one piece of hardware, had developed a fault, and you could take it out of the loop, and you could rely on the other 3. If one of those then started giving you incorrect data, you could take that one out of the loop, but then you were only left with 2. And then if they start to disagree, you don't know which one's correct. And so at that point, there was what's called a mission abort condition. Basically meant if you lost any computer, you turn around and you start coming home right now, because if you've lost one, you can't afford to lose another one, because if you lose another one, you're down to 2, and then if they start disagreeing, you don't know what to do with it. You're going to be in a lot of trouble. But if all 4 of those primary computers suddenly start giving you completely different information, they would fail over to the 5th. And the 5th was running the same software, or no, it was running software built by a different contractor to the same specification. There was no relationship between the two completely independent suppliers, because their risk analysis calculations said, even if there is a catastrophic bug in both of these implementations, the odds of it being in the same place are effectively 0. So even if one of these computer systems has a catastrophic bug that's going to go off halfway during launch, the other one probably doesn't have a problem in the same place, which is a really interesting way of kind of hedging your bets and acknowledging that neither of these systems is going to be perfect. Now, for the first couple of missions, the shuttle actually flew with a 6th computer on board that wasn't running anything, because the reasoning was if they lost one, they could patch the code across, put it onto the 6th one, get that plugged in up and running, and that one would take over so that they would not have to abort the mission. They eventually stopped carrying it because after 6 missions, it had never been used. And, you know, the Congress, Senate, the people who control the budget for NASA were like, you need to stop flying spare parts because it's costing the taxpayer like $1 million per pound to send spare parts into space, and you're never using them. Now, as it turns out, the shuttle never had a computer failure. The computer on board the shuttle was 100% reliable. But there were other things caused by this attitude to risk of that didn't go wrong, so we should stop worrying about it because it didn't go wrong last time, so it's probably going to be fine, which would go on to have really tragic consequences. Now, human beings suck at risk. We are terrible at anticipating how risky certain kinds of behavior are. Anyone here afraid of flying? Because, you know, lots of people, they find flying, they don't like it. And then they land at the airport, they get in a taxi, and they're like, the danger is over. So I'm not doing you any favors when I tell you, you are way more likely to get killed in the taxi than you are in the airplane, because road accidents, in terms of, you know, per hours of participation, being a passenger in a car is way more risky than being a passenger in an aircraft. But we associate being in a car with familiar everyday stuff we do every day. You know, we go in our car, we drive to school, we drive to the shops, we drive all over the place, we go see family. It's just the car, you know, it's not dangerous. Whereas going in planes, most people don't go in planes very often. So when they think about planes, they think about the stories they've seen on the news and on Hollywood movies and TV about aviation disasters. And because those are professional storytellers trying to scare the crap out of you, that resonates. And so we think cars are safe because our experience of cars is based on what we do, and we think about aircraft, and our experience of aircraft is often based on stuff we've seen happen to somebody else, and of course it doesn't make headlines unless it's bad. You know, no one ever goes on the news and says 80,000 flights landed perfectly safe. That's not news, that's just business as usual, you know. So when you think about something like installing a new piece of software, you're rolling out an upgrade across a whole network of systems, and it is kind of part of the process that everyone gets ready, like we're doing a big upgrade, you know, it might go wrong. We're going to plan for this, we've planned for that, we've got a backup, we've got a failover strategy, we've got all this kind of stuff. And you think through all of the failure conditions and come up with a plan for what you're going to do if those things happen. You roll out the new system, there are probably some bugs. You say to all your users, like, you see anything weird? We just launched this big upgrade. You see anything weird, just let us know so we can jump on and we can fix it. But then after a couple of weeks, you've fixed most of the things that you didn't think about. Everything kind of settles down, and that's when things get interesting. There is a bathtub curve shape, which is a plot of the number of failures or defects you get in a system against the operating lifespan of that system, and it's called a bathtub because it looks like this. Comes down, goes across, and goes up again. And this hides something really important. There are 3 kinds of defects that you get in systems. You get what are called early life cycle defects. This is, in mechanical systems, these are the parts that weren't installed properly. In software, this is the edge cases that you missed, that you never realized until you went into production that that was even a thing that could happen. Then there are what are called the random defects, which is just stuff goes wrong. every day for no readily apparent reason. This computer doesn't work. Why not? I don't know. It's been working for 4 years. Today it decided it's not going to work. All right, we better replace it. And then we get end-of-life defects. Now, in mechanical systems, this is where pieces start to wear out. You know, bearings wear out, valves wear out, hinges wear out. In software, this is the point where people stop giving a crap because they're going to do a new one any day now. And so like, we're going to stop maintaining. We're not going to fix that bug. It's all right. The new system will be here in 6 months, 9 months, 2 years, 5 years. Is anyone familiar with Brandenburg Airport in Berlin? That was supposed to open in 2008, and it didn't, and it didn't, and it didn't. And every 6 months, I guess somebody in Berlin must have been like, we should extend the metro system to Tegel Airport. And they went, no, Brandenburg's opening any day now. And so for 14 years, the main airport to the capital of Germany, you had to get the metro as far as you could, get off and wait in the rain next to the lawnmower shop for a bus to take you to the airport. And that's a classic example of, no, this airport is end of life. And it ran on for another 14 years. But in software, this is why systems eventually, software doesn't wear out. We get unsupported operating systems. We can no longer install the latest security patches for this component or that component. But really, this is just we decide that the software is no longer being maintained, and then things start to kind of go downhill. So we have these 3 different kinds of defects. And this is the kind of attitude we have to it. The new system, hey, stay alert, watch out, things might be weird, relax and everything's fine. And this means that during the relax, everything's fine, we think the number of defects is going to continue going down because we think that curve is going to go all the way to 0, but it doesn't. And this gives us a lax attitude to failure. When the Space Shuttle was first commissioned and launched, there was an extensive set of launch control protocols and criteria, and one of those was the Space Shuttle Weather Launch Commit criteria. You couldn't launch the shuttle if it was raining. You couldn't launch the shuttle if the wind speed was above a certain level, if there was lightning, if the maximum temperature was above a certain level, but they didn't have a minimum temperature. There was nothing in there about it being too cold to launch the Space Shuttle. And in February 1984, they did a launch where it was 13 degrees Celsius outside. Now, this is in Florida, which, you don't think of Florida as somewhere that gets cold. It's 13 Celsius, and they're like, is this safe? And they talk to all the suppliers, and all the suppliers are like, it might be safe. We don't know. And yeah, they got into this weird thing. There's so much pressure to keep flying the shuttle because they need to keep putting payloads into orbit, launching satellites, because that's where the money for the space program kind of came back in from, that these, the suppliers, the contractors who built the components were like, we don't think it's a good idea, but we're not going to be the ones you blame for stopping it. So put down on the record that we thought it was a bad idea, but then you go and do it anyway. So they launched, 13 degrees, off they went. A year later, January 1985, it was 10 degrees outside when they launched the shuttle, and they said, is this a good idea? And people were like, well, it went okay at 13. Like, I guess 10 might be all right. It's not a good idea, but, and there was this kind of, YOLO, try it and see what happens. And then January 1986, it was 3 degrees. The Space Shuttle launched, and the rubber seals on those external rocket boosters, it turned out they were brittle. Below 5 degrees Celsius, the rubber stopped flexing. It would stay fixed in place. It wouldn't seal the gaps. There was a catastrophic explosion, destroyed the spacecraft, killed all 7 astronauts on board. Now, the person who correctly identified the cause of that explosion was this guy, Richard Feynman, the Nobel Prize-winning physicist. He was invited to be a kind of external advisor on the investigatory board for the Challenger disaster. And one of the things, his observations, NASA did not like what he had to say about this, but they published his observations as an appendix to the official report. And one quote from that, he said, we found that the certification criteria used in flight readiness often develop a gradually decreasing strictness. The argument that the same risk was flown before without failure is accepted as an argument for the safety of accepting it again. Now, has any of you who drive a car, you ever had a problem with the seatbelt on your car? And it just won't do up, so you book it into the shop, but they can't see you till next week. And so you go out without your seatbelt on once, and it's really scary. And you're like, I'm going to die. And you don't die. And you get home, and the next day you're like, oh, I need to go to the store. All right, the seatbelt's still broken. Well, I didn't die yesterday. And by the end of the week, you've been driving around without a seatbelt the whole week, and you're like, I don't get the big deal about the seatbelt, you know. I've done it for a week, I'm absolutely fine. And of course, we don't wear seatbelts for driving, we wear seatbelts for crashing, because that's when they help. But if you're not crashing, it's difficult. You have to keep obeying the criteria, even though the circumstances they were developed for are not actually in effect right now. Now, when we think about applying these same kind of lessons to the way that we design and build software, the attitude to risk, this idea of it didn't go wrong last time, so maybe we're being too careful, we're not worrying about it. We live in a remarkable age where, thanks to cloud infrastructure, we don't need to worry about things until just before they go wrong. With modern cloud systems, you get unexpected load. It's like being able to, as your car is going into the concrete bridge, you're like, crap, time to buy seatbelts. And you put your credit card in and boom, there it is, just before you hit. We can do this, We have the ability to go, building's on fire, quickly, Amazon, fire extinguishers. And we can provision all this kind of infrastructure within minutes, sometimes. I've been working long enough that I remember if we thought we were going to have a traffic spike, 3 months earlier, you would order more servers. And you'd have to kind of eyeball, how big do we think it's going to get this Christmas? All right, we'd better get another Dell PowerEdge with like the 16 gigs of RAM, and it would come in a box 6 weeks after you ordered it. You'd put it in a rack, you'd get it up and running, and it'd sit there and it would do nothing, and you'd hope that when the spike came, one, you'd hope it came, because otherwise you wasted all that money on a server you didn't need, and you'd hope it wasn't any bigger than you were expecting, or you'd wish you'd bought a bigger server. Today, we're like, nah, just scale it up. That's absolutely fine. Now, we can design systems that are tremendously resilient. We have a reverse proxy that's like, well, actually, we're going to replicate everything here across 2 geographic zones, and each one's got a load balancer with a bunch of web servers. We got active replication. The single point of failure that I've seen in more cloud systems than anything else is the MasterCard at the bottom that's paying the bill. Because you can have as much replication and web servers and database shards and everything, but the second Amazon can't get your money, they start switching things off. And for a long time, there was no way of saying, actually, here are all the different credit cards we can possibly think of. Some of the worst downtime incidents in my own career have been caused by corporate MasterCard limits. So you need to anticipate the things that could go wrong. And if you look at the history of massive engineering failures that make the international news headlines, in almost every case, it's people who thought it was going to be fine because they were no longer taking a vigilant attitude to risk. And the most recent example of this is the British Post Office. In 1995, Post Office Limited, which is the private company that runs the postal system in the UK, they commissioned a new IT system called Horizon. There was a contractor working for, I think, Fujitsu Siemens were the contractor who were coordinating this. They ran a pilot scheme. In 1999, they rolled out Horizon across 10,000 post office branches. And within a couple of days, the staff in these offices started saying they were reporting discrepancies. The numbers weren't adding up. The money in the till didn't match the money in the computer system. Now, I want you to imagine you've just rolled out a new IT system across 10,000 sites, and the people who've been working in those branches for 10, 15, 20 years, they are saying to you, your computer system is reporting the wrong numbers. The money is not adding up. You need to fix it. What would you do? Because you know what they did? They prosecuted them for stealing. They turned around and went, no, the computer system is right. You will give the money back or you will go to jail. And I mean, it sounds funny. It's true. It is the most disgusting, miscarriage of justice. Employees were told, if you pay back the missing money, then we will not give you a criminal record. People cashed in their life savings. People mortgaged their homes. Some people couldn't. They were prosecuted. They had charges pressed against them. Some of them went to prison. In 2019, 550 post office branch managers filed a class action lawsuit against the Post Office Limited, which was eventually settled for 58 million pounds. Now, in the transcript of that lawsuit, this lady, this is Paula Venables, the chief executive of Post Office Limited, who's also a Church of England reverend until they told her she had to stop. Does she look evil? She said, the message the board and I were consistently given by Fujitsu from the highest levels of the company was that while, like any IT system, Horizon was not perfect and had a limited lifespan, it was fundamentally sound. Not perfect, limited lifespan, but you're going to jail because the computer doesn't agree with the amount of money left in your shop at the end of the day. The judge, the High Court judge who presided over it, Honorable Mr. Justice Fraser, he said the Post Office defense amounted in reality to bare assertions and denials that ignore what actually occurred, the 21st century equivalent of maintaining that the earth is flat. Now, British High Court justices, they are normally very, very dry. This is like him completely losing it in the judgment, you know. Now, this has finally been overturned. The convictions have been overturned. They're blaming it on corrupt data. Now, you know, if we accept that data is imperfect, then surely the people making decisions based on the corrupt data are the ones who should be liable. This has gone down as one of the biggest miscarriages of justice in British legal history. Now, you know, given the consequences of the decision, I find it unbelievable that the people responsible trusted the new computer system over the word of their own staff across this many incidents, across this many different disconnected branches and situations and people. Now, if you've ever worked any kind of help desk, you've had the thing where you know the person on the other end is lying because they ring you up and they say, "Where are my files?" And you say, "What files?" And they're like, "The files that I put on the network." And you're like, "You didn't put any files on the network." But you're like, "You know what? All right, all right. Let me go and check the backups." And you put the phone down, you make a cup of coffee, and look out the window for a bit, and then you phone them back. "I'm sorry, I've checked the backups, there's no trace of the files." But, you know, this kind of stuff happens all the time. People are like, "I definitely put the files through, I definitely submitted this, I definitely clicked save," and you're like, "I didn't," yeah, you know. But if someone was going to jail, I'd actually check the backups, you know? If someone was going to jail, I'd be like, "No, let's go through every single line here. Let me check your hard drive. I'll check the networks. I'll check all the stuff." And at the end of it, if it was literally one person saying they'd done this and a computer system saying done something, I'd be like, "We don't know." I wouldn't be like, "You're lying and now you will go to prison for it." Now, sometimes the consequences of not anticipating the role of the end user in a system can have tragic results, but sometimes they just have everyday frustrating results. How many of you are familiar with this, you know, the thing where you go to log into a website and it texts you a code, and this is good. This is two-factor authentication. Security is important. I have a friend who lives in central London, not far away from where I am. She has no mobile phone reception in her house because it's an ancient Victorian building that's kind of down in a valley. So for her to sign into online banking, she goes onto the thing, types in her laptop, grabs her phone, and has to run out into the street round the corner and hold her phone up. And when she gets the code, she has to run back in and type it in because the code is only good for 60 seconds. And the people who built the system, it works perfectly. You send the text message, you check the text message, you type it into the website. Awesome, you know, works every time. And you say to them, "Yeah, but what about someone living in a Victorian house in a valley?" And they're like, "That's not a software problem, we can't fix that." Because it's not systems thinking, it's software thinking. They haven't taken that step back and gone, "All right, the phone works, the network works, the website works. What else might cause this thing to fail?" Any system, every system I've ever built has gone into production, and within about, I don't know, a week, someone has thrown something at it that I'm like, "Wow, we didn't think of that happening." And I found this video recently which demonstrates this beautifully. This is the Tesla autopilot going down a road, going traffic lights, traffic lights, traffic lights, traffic lights, traffic lights, because it's following a truck full of traffic lights. And it never occurred to anyone that there might be traffic lights on the public highway for a reason other than traffic control. I've seen similar things. A lot of ice cream trucks around where I live, they have a stop sign painted on the back so that you know not to kind of run over little kids who are getting ice cream after school. And the Teslas will pick them up and they'll stop. And the ice cream truck will go off and it'll start again and it'll stop. Now, end users are frustrating because they don't use the system right. Like, they are ingenious. You give them a tool, and they will figure out ways of using that tool that were absolutely not how you intended it to be used, because end users are ingenious. They got stuff to do, and they are going to figure out a way of doing their jobs. I had a couple of friends years ago who worked for a company who made laboratory equipment who were paranoid about industrial espionage to the extent that they blocked attachments. You could not send email attachments in or out of the company. And they got engineers all over the world going into universities and hospitals to fix, really, really quite expensive, sophisticated kit. And they're like, I need a firmware patch. So they'd phone one of their buddies back in the office and be like, hey, I need the 27.6 firmware patch for this one. And what they do is their buddy back in the office would sign into Hotmail, go into the drafts folder, compose an email, attach the attachment, and not send it. And then they'd ring you back and go, hey, it's in the drafts folder of the shared mailbox that every engineer in the company knew the password for. They never sent the email, because that would be breaking the rules. The fact there's a Hotmail drafts folder full of firmware upgrades and stuff, well, no one said that was illegal, so, we are playing by the rules. Now, sometimes technology goes wrong in ways that looks like a bug until you dig a little deeper. This thing here is it's a mathematical shape called a Lorentz attractor. It comes from this wonderful field of chaos theory and fractal geometry, which is something I really love working with. And it's named after this guy, Edward Lorenz. He was a meteorologist. He was a weather forecaster. He was one of the first people to look at whether you could use computers to predict the weather. And he did it using this. It's a computer called the Royal McBee LGP30. Had 128K of RAM, 120 kilohertz CPU clock. It weighed about 350 kilos. And he built a little weather simulation system that ran on this thing. And his weather simulation, he just plotted metrics of atmospheric temperature at different points somewhere on a kind of little simulated world. We're talking really, really simple simulation here. And then he'd run his simulation, and it would print a graph. And I say print, it was a teleprinter, so it would actually print the temperature by just going space, 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 dot, space, 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 dot. So he'd get these little graphs. And one day the story goes that he got halfway through a simulation, the computer crashed, so he took the printout of the numbers, typed them back in, and set the simulation running again. And it went the same up to a point, and then it deviated. And it started doing something different. And he's thinking, this is a computer. Like, where is the idiosyncrasy? Where does the difference come from? And what he worked out is that internally, the Royal McBee was storing 6 decimal places of precision, but it was only printing 3 of them. And it was that difference, that 0.000678, that led to him starting to discover what would become known as chaos theory. Systems which are incredibly sensitive to tiny, tiny differences in their initial input. He says that he knew that day, the day he discovered it, that we were never going to be able to do long-range weather forecasting using computers. And the intervening 50, 60 years have basically proved him right. But that little computer glitch, that difference between the printout and the memory, spawned a completely new wing of science. Chaos, fractal geometry, all that stuff kind of emerged from that discovery. Now, if you've ever sat out in a field on a sunny day and you've kind of looked up and seen clouds and your brain is trying to fill them in and turn them into shapes, what is going on there is we have pattern recognition routines that have evolved into the way our brains work. We can recognize friends, we can recognize predators, we recognize family, our social community. And we have started teaching computers to do the same thing by taking a convolutional neural network, which we don't quite know how it works, but we know what it does. And we feed it a whole stack of labeled photographs, and it goes through, and it's, the terminology here is difficult. Figures out is maybe the wrong word. It's that famous Edgar Dijkstra quote, asking if a computer can think is like asking if a submarine can swim. But we feed a bunch of data into that thing, and eventually what we get at the other end is a system that refuses to play animation, which is always entertaining. There we go. And comes out the other end and goes, oh yeah, I've decided that this thing here is, there we go. That, by the way, is a feature of the M1 Mac with Apple Silicon, is sometimes it doesn't play PowerPoint videos. It does a lot of other things well, but that one doesn't work, and I still haven't figured out why. So we've built something that can recognize dogs, which might not sound like it's difficult, like, how difficult is it to tell the difference between a dog and a cupcake? Might be harder than you think. But then, the end users come along, and they're like, someone built a dog detector here. Now, I was out in Refn on Sunday, and there's a lot of people take their dogs up to Refn, and I quite like dogs, and so I run the dog detector over this photograph I took of Refn, and it comes back, and it says, sorry, we didn't find any dogs in this picture. But then I do the end user thing. I'm like, turn the dog detector around, and turn it into a dog amplifier, and turn it up. And the computer goes, what are you doing? And I'm like, turn it up. And it says, are you sure? And I say, turn it up. And he goes, this is a horrible idea. And I'm like, turn it up. There we go, look. And I'm like, increase the amplification. The computer's going, this is a horrible idea. This is not what the neural network was designed to do. And I'm like, no, come on, maximum power. And through the creative misuse of serious computer science, we have created a new form of art that can take photographs of something completely innocuous and turn them into weird kind of psychedelic dream sequences with lots of noses and eyes and teeth everywhere. Now, I love the misuse and misapplication of technology because it is so ingenious. Sometimes it leads to delightful whimsy. Sometimes it leads to Hotmail drafts folders full of firmware updates and stuff. But sometimes it can lead to some real social change. I grew up in Africa. I spent my childhood in Zimbabwe. I was born in Kenya. We used to go on holidays when I was a kid where we'd get in the car and we would just drive for 3 or 4 hours down roads that look like this. You know, no civilization, no tarmac, no streetlights, nothing. And every once in a while you'd see in the distance there'd be a little hut by the side of the road somewhere, and it was always painted bright red and white, hand-painted Coca-Cola logo. And there'd be someone in there, I don't know how, but they always had like a crate of ice-cold Coca-Cola. And I went back to Africa a couple of years back for my cousin's wedding. I was in Zambia, and there were bits of it that hadn't changed in 20 years, except the red and white hand-painted signs don't say Coca-Cola anymore, they say Vodacom. Because since the turn of the millennium, Africa has experienced a communications revolution. Trying to run regular telephone networks across Africa was never going to work, because you need 3 things to do that. 1, you need a dense population of people. 2, those people need to have a lot of money. And 3, the government has to have your back if someone turns up in the night and steals all of your wire. For various complicated reasons, Africa is very sparsely populated. A lot of the people who make up the population are not terribly affluent. They don't have a huge amount of disposable income. And government corruption is rife across parts of southern and sub-Saharan Africa, which means you spend a fortune laying copper cable along the side of the road. You come back in the morning, the cable is gone because someone has taken it and sold it for scrap. And so for whatever reason, Africa didn't take off until cellular networking came along. Because mobile phones are a game changer. You don't need the infrastructure. You can put a bunch of masts up on top of a hill and suddenly 300 or 400 people can be reached by that one cell phone tower. If you went here, this is Nairobi, capital city of Kenya. If you'd visited here around about the year 2000, Nairobi's a modern city. Restaurants, banks, entrepreneurship. There are even a couple of tech startups running out of there as early as 2000. But you could drive a couple of miles outside of Nairobi and you'd find people who had never made a phone call, let alone seen a computer. People who had no idea what the internet was or why it would matter to them. So as they started rolling out cellular networking and putting in the infrastructure, one of the challenges that they had there was, how do you roll out mobile phone networks to people who don't have bank accounts? 80% of the population in Kenya, pardon me, is what was known as unbanked. They don't have any kind of banking, no savings, nothing. They live cash in hand. And what kind of happened is each village, somebody would get a mobile phone. And effectively, that would become like a little startup business for them. They'd have a Nokia phone. And if you needed to make a call, you'd go and see them. You'd give them a little bit of cash, they'd let you make a call. And when they got enough cash, they would get on their bicycle and they'd go into town and they'd buy a Vodafone top-up card or a Vodacom top-up card. They'd buy credit. Everything was prepay because nobody had a bank account. Then the users realized that the thing you needed wasn't actually the top-up card, it was the code, the serial number that would activate the credit. And this spawned something remarkable because a lot of places, the kids would, grown-up kids would go and work in the cities and their parents would be way out in the country in the villages. And so someone would get a job in Nairobi. They'd be working in a factory or working in a bar or something. And previously, to send money home, either they would have to make the trip themselves, take them about 4 or 5 days, or they would put the money in an envelope and try and find somebody they trusted who was going in the right direction and hope it got there. But when they figured out that they could transfer mobile phone credit, they would ring the telephone person in their parents' village and they'd be like, hey, I got 10,000 shillings of top-up for you. And they'd read the number out. So they'd take their cash from their job, they'd buy the card, they'd read the number out. Guy back in the village or lady back in the village would top up their phone with 10,000 shillings. And the next day when mum comes in for groceries, they'd be like, hey, your son sent me 8,000 shillings, minus a, consideration, because you've got to grease the wheels of commerce. But this was a game changer because it meant there was suddenly a reliable way of transferring money that didn't involve carrying cash. Now, shortly after that, they launched a friends and family system, which meant you could use a text message to send top-up from your phone to someone else's phone. Now, this isn't telephone banking. This is literally just transferring mobile phone minutes of call time credit. But suddenly, people started using this as a form of currency. They would, go into the store, they'd buy some groceries, they would pay by sending a text message with 500 shillings of credit. Storekeeper would go out for beer after work, they'd buy their beer with credit. Next day, the guy running the bar needs to get his bicycle fixed. He goes to see the place that fixes bicycles, sends him a text message, there's the credit, it starts circulating. People are using this as a de facto form of currency. Now, this is the point where Vodacom might have gone, this was a terrible idea. We launched mobile phones in Kenya and no one's making any phone calls. This is not what we designed the system for, but that's not what they did. What they did instead was they went, there's a really interesting opportunity here. Maybe we can actually take what is already happening here, that this has been created by end users innovating with the tools we gave them, and turn this into something that we can actually use. And so the product that they created was a thing called M-Pesa, mobile payments. M for mobile, Pesa is the Swahili word meaning money. And M-Pesa had a network of authorized agents, so there'd be someone in your village who, if you needed to, you could take your M-Pesa in and you could cash out. You could get proper cash back. But most people didn't. They just circulated M-Pesa airtime credit, and this became the de facto currency of the entire Kenyan economy within about 2 or 3 years. It has represented, I saw recently, it said a path out of poverty for something like 250,000 people, just because they had a reliable way of receiving money and hanging onto it that didn't involve cash. Now, this only worked in Kenya. They tried to roll it out in Afghanistan a few years later. It didn't take off. They tried it in Romania. They tried it in India, Pakistan, Tanzania. It's still, there's a couple of places in Africa. Ghana, they use it a little bit. Tanzania, they use it a little bit. In Uganda, it's still available. In Kenya, it is ubiquitous. Trying to shut down M-Pesa in Kenya now would be like telling Europe they're not allowed to use MasterCard anymore. It's that relevant. And it only exists because the users used the product wrong, and the managers of the product company went, this is interesting. And they didn't say, no, we're taking your phones away. They didn't shut the system down. They didn't change the terms and conditions. They learned from what they hadn't anticipated. They looked at something which could have been construed to be failure and went, actually, this is really interesting. There's something here we could not have anticipated. So go out there, build the systems that you build, do good work, write tests, make sure stuff works, cover everything you can think of, but don't ever make the mistake of thinking that you know better than your own users. Because once stuff goes into production, it gets out there, real people start using it, failure is always going to be an option. Thank you. We have a couple of minutes for questions, folks. Does anyone have any questions? If not, I know that the next thing on the program after this is the party. There will be beers, there will be snacks, there will be comedy, assuming that my co-hosts have finished writing it while I've been up here talking about mobile phones and space rockets. Stick around, folks. Enjoy the rest of the evening. Enjoy tomorrow if you're not staying this evening. I will see some of you later on at the party. Have a great time.